Hi, everyone. I'm very happy to have all of you here. And yeah, we are all here today to hear Jonas Huebotter's talk about test time training agents to solve challenging problems. He's a PhD student at ETH Zurich and does a lot of work regarding transductive active learning. The agenda for today will be that we will start first with his talk, and then we will do a moderated Q&A session. For everyone for whom this is the first Heidelberg AI event, Heidelberg AI is a student-led event series for AI enthusiasts, students, and researchers to exchange ideas and to get to know each other. We are part of the larger Heidelberg AI ecosystem, where we collaborate closely with the Alice Unit Heidelberg, the NCT Data Science Seminar, and Helmholtz Imaging. We are part of the German Cancer Research Center, and we are student-led, and all of the organizers whom you can see here are part of the medical image computing division of the DKFZ. Finally, if you are not aware, we also have a LinkedIn page where we announce our new events, and please feel free to follow the QR code. So, getting back to our speaker. Jonas Huebotter is a PhD student in the Learning and Adaptive Systems groups at ETH Zurich, where he works closely with his supervisor Andreas Krause. Prior to this, he obtained a master's degree in theoretical computer science and machine learning from ETH Zurich, for which he also received the ETH medal and a bachelor degree in computer science from the Technical University of Munich. Much of his recent work focused on transductive learning, and I'm really excited to have him talk at this event about his work there. So just for starters, most of standard machine learning uses induction, where from observed training cases, general rules are learned, and these are then applied to test cases. In transductive active learning, the reasoning is directly performed for specific test cases based on specific training cases. So, without further ado, I hand over to our speaker. Please give him a warm round of applause.
Thanks, everyone. Thanks, Karsten, for the very kind introduction. I'm super excited to join you today. Unfortunately, not in person, but at least online. Also looking forward to the discussion we will have later today. So to start off, I will talk a little bit about our recent work around test time training and putting test time training in the loop, so test time training agents, and how they can be used to solve challenging problems. And so given that Karsten already introduced me, I'm going to skip this. I also want to thank all of the collaborators that I have worked with on the projects that I will talk about, and I will acknowledge them more along the way. So my agenda for this talk was quite simple. I basically want to make two statements and argue for them extensively. So the first statement for which I would like to argue in this talk is that test time training, and test time training meaning kind of the transductive way of learning, which Karsten mentioned, that test time training can enable models to outperform globally trained, so inductively trained models, even in distribution. So without any extra distribution shift or any extra data that you provide to them. And then the second statement for which I would like to argue is that test time training enables models to continue learning and improving at test time and eventually really solve quite difficult tasks, which initially models were not able to solve. And just as some nuggets for to keep in the back of our mind while we go through the first part of the talk, we'll talk a little bit more about test time training as a concept. I want to kind of briefly mention some applications of test time training, which we'll get back to later. So one is some recent work by a great group of people at MIT that uses test time training in a few-shot learning setting, among other tasks for the ARC challenge. And then another area which I will go into is test time training for high-dimensional robotics tasks. And then finally, test time training for reasoning. And all of these are really tasks which are arguably quite difficult. I'll get more into later in what way they are challenging and difficult. And all of these tasks present opportunities for test time training to improve models. But now in the first part, I want to talk more generally about test time training. And I want to start with a nice quote from Vladimir Vapnik, a famous statistician who coined the term transductive learning. And basically his definition is given in this quote. So he said, when solving a problem of interest, do not solve a more general problem as an intermediate step. Try to get the answer that you really need, but not a more general one. So he says, instead of just solving all problems that you can possibly conceive of at once, just try to solve the problem that you are actually interested in solving. And this is kind of a key quote that will be the key motivation for most of what we'll talk about in this talk. Now I want to start with the standard pipeline machine learning, which all of you are probably very familiar with. Typically, you start with some training data. Let's focus on the supervised setting. So you have some inputs X and some labels Y, and then you train a model on this data. And then finally, for a given test input X star, you will use this model to make a prediction. Now, of course, for this, you will have to know your test instance X star at test time. So this is typically separated, this process, into two stages: train time. And then after train time is completed, you freeze your model, you don't change it anymore, and then you deploy it at test time, where then given a test instance, you use this model to make predictions. Now, of course, at test time, this test instance has to be known to make predictions. So an alternative approach is to actually, at test time, use this test instance to inform the model, which we will use for then later downstream making a prediction. And this is in general called test time training. So now to make this a bit more concrete and kind of come up with a working definition of test time training, at least for the beginning of this talk, we will consider some data set, as I mentioned, of inputs and outputs. And then the kind of standard baseline is global training or inductive training, which trains a single model F and then uses this model to predict. And test time training, on the other hand, trains a specific model, which we would call FX. So that model is specifically trained for the input X, and then uses this particular model for the prediction. Now, a very natural question is whether this form of test time training can improve the predictions over a globally trained model, even if its predictions are measured in distribution of the training data. So the globally trained model was trained over that same distribution that we sample test inputs from now. And also while using only the data set that we used for the pre-training. So not giving it any kind of extra data that would give it an advantage. Right? So the typical thing would be to take local data from the data set at test time. So given an input X, you will find, based on some embedding space, you will find local data, similar data in your training data set, and then train your model at test time on this local data from this neighborhood to yield the specialized model FX. So this is really a big question because traditionally, and also initially when test time training was proposed, but also traditionally fine-tuning was often performed in transfer learning settings where you took a model that was trained on distribution A, and then you wanted to transfer the knowledge to distribution B. But nowadays, when we have foundation models, more and more tasks seem to be in distribution of these models. So it's a natural question to ask, can these models benefit from additionally specializing to a particular task? So this was really the question that we started off with in this work, which we'll present at a workshop at NeurIPS later this year, was really why can TTT work in this kind of very natural in distribution setting? And we came up with one model where it can work, and I'll walk you through it. It's quite simple. So we will assume the existence of an S-sparse so-called concept space, which lies in D1 dimensions. And then we will assume that the target function, which we're aiming to learn, is linear in this concept space. So that our function f of x, f star of x, which we aim to learn, is a linear function in these concepts. So I don't know if many of you are familiar with this, but this is commonly called the linear representation hypothesis. It's also often used in classification settings like next token prediction language models, where people have observed that to some extent, for example, language models learn some kind of latent concept, not explicitly, but implicitly learn a representation of latent concepts, which can be linearly composed. So famous example are with king and then adding female to turn that into queen, etc. So this is called the linear representation hypothesis, and we're basically borrowing this assumption here. Now, the key aspect here is that this concept space is extremely large. D1 is extremely large, and this is way larger than kind of the size of any hidden layer in your network, way larger. And the other key aspect is that the activations in this concept space are sparse. For any given input, you will have only a few active concepts. For example, for king, you would have qualities like royal and male, etc. Now, the final assumption that we'll make is that our model learns some dense, potentially exponentially smaller approximation of this concept space. And we'll call this the feature map, which lives in D2, and D2 is way smaller than D1. And now we can use some very powerful theory from compressed sensing, which says that given that our concepts are sparse, activated concepts are sparse, there exists a polynomial time algorithm which basically compresses and decompresses these sparse concepts into an exponentially smaller dense feature vector, right? So there's lossless compression and decompression happening here. So in other words, we're able to represent losslessly, at least in the ideal case, losslessly represent all of our possible combinations of active concepts with this much smaller, exponentially smaller dense feature vector, right? And this kind of motivates this study behind the linear representation hypothesis, that models exploit this. It's also called superposition, exploit this ability to superimpose concepts into this dense space to represent this extremely rich family of possible concepts. Right, so intuitively, this is illustrated here. So you would have an input X, and then we posit the existence of some concept space where features are sparsely activated. So for example, lion and king. But then the actual features that you would see in the neural network are some dense superposition, so linear superposition of these features into a much lower dimensional feature vector. Now, to understand how test-time training behaves, we trained some sparse autoencoder for ImageNet and kind of learned the concept space, which we can actually probe. So we cannot look into the concept space, which we assume to exist, but we can at least try to estimate it. And then we made some observations. So the first observation that we made, and that's similar to what prior work also observed, is that the learned features of the model, they yield similar neighborhoods when you compare to the neighborhoods that you would get in concept space. Then the second observation that we made was that among a test point and its neighborhood in the feature map, the true function f star can be approximated by a sparse linear function in the concept space. And this is actually surprising. Why is this surprising? Well, in principle, the number of potential concepts that could support your function among your test point and your neighborhood is s times the size of your neighborhood plus 1, right? Because these are all possible potential concepts. But what turns out to happen in practice is they all overlap to a large extent among the neighborhood, meaning that actually the function that you need to learn across the neighborhood has not s times size of your neighborhood many concepts, but just s. It's very sparse. And then the third observation that we made was that if you perform test time training in the feature space, so the normal way of performing test time training, this implicitly adjusts coefficients based on only a few concepts. So in the sparse space, based on only a few concepts relevant to the test task. And this is, in some sense, also surprising, but it's also predicted by kind of a rich family of prior work on implicit regularization and sparse recovery. So we took these three observations, and especially observation 2 was quite surprising to us when we found this in practice. And then we looked at what does these observations imply. And then it was kind of nice to show that under these observations 1, 2, 3, and if you assume your data is sub-Gaussian and you have some standard regularity conditions in standard from the literature of sparse recovery, then you have that for any x and a sufficiently small neighborhood size so that the observations 1, 2, 3 actually hold, you have this statement, which basically says something very simple. It says that the error for your prediction of your TTT model that is learned in the dense feature space, so the actual normal TTT that you would perform, the error of this is bounded by this term on the right-hand side, which is also the minimax optimal rate from sparse recovery. And this decreases with increasing size of neighborhood quite quickly because the numerator only depends on the sparsity, which is very small, and the log of the number of concepts. So very favorable term. Now to comparison, we also looked, okay, what does this mean for global training under the same assumptions? And it was actually quite easy to construct an example where global training completely fails. So under the same assumptions, there exists an instance where the function is actually constant. It's just 1, where the error of the global model, so 1 global parameterization over your dense feature space, is 1 minus d2 over d1. And this is kind of intuitive because as one would expect, if the global model is not underparameterized, so d2 equals d1, the error of global training is 0, of course. On the other hand, if you have this trivial global model, which is just if v global is 0, it's a 0 vector, then you always predict 0. The error of that is 1, right? This is kind of the worst case error. And then as the model size d2 shrinks, the error of the global training increases towards 1. And as the number of distinct concepts d1 increases, the error of global training also increases. And that approaches 1 as d1 goes to infinity. Right? So it's a kind of a very natural example. And this shows that kind of even under these kind of simple observations, test time training can yield a kind of significant boost over global inductive learning. So this is kind of the key takeaway. Test time training efficiently learns the meaning of exponentially many concepts from data. So efficiently meaning you don't need many samples. It scales in your neighborhood size and quite favorably. And you can learn the meaning of exponentially many concepts because we can kind of leverage this feature of sparse recovery, which allows you to compress information of exponentially many concepts into a manageable sized dense feature vector. But intuitively, so this is a lot of kind of talk of theory and assumptions and observations, etc. But intuitively, I think what happens is quite simple. I want to illustrate this quickly. So let's say your goal is to fit this black curve and you have a restricted model class. So you cannot actually fit this curve exactly. Let's say you're limited to linear models. Well, in this case, you can fit a linear model and will capture the trend of this curve. But it obviously will not be perfect. So what test time training enables you to do is to locally fit several instances of this model. And we actually have not increased our model class at all. We're still limited to linear models, but the function class, the effective class of functions which we are able to model in this way is much richer than just linear functions, of course, right? So in this sense, test time training allows you to temporarily forget the irrelevant kind of pre-trained knowledge. And this kind of frees up the capacity to learn the relevant concepts for your prediction at test time at a higher resolution. And in this paper, we called this process specialization after generalization, where generalization is this initial phase, pre-training phase, which is quite important, where you learn the concepts. And then specialization later allows you to narrow in on learning the precise meaning of the concepts which you have, where the concepts you have learned in the initial stage. So then the final thing in this project, which we wanted to understand, was when this simple form of test time training would actually work. And so we ran this across MNIST, ImageNet, and language modeling and performed a scaling study where we varied the size of model and looked at the error. And we saw throughout, this was really the important takeaway here, that test time training locally improves predictions for the underparameterized models. right? So precisely the models which are not able to fully fit your curve initially. But this improvement diminishes, and eventually there stops being an improvement as the models become over-parameterized. So this is kind of the first block on what I wanted to talk about on test time training itself and why test time training may work. And then I want to move on to the second part where I want to talk about test time training agents and how you can use test time training to continue learning at test time and solve hard tasks. And I want to start with a quick warm-up, which is based on the paper from the great folks at MIT, which I already mentioned initially. And this warm-up will be on few-shot learning. So in few-shot learning, each test task comes along with demonstrations, right? So these are demonstrations that show how you should attempt to solve your task, kind of what kind of distribution your test task comes from. And so this group of people at MIT, they applied this, among other benchmarks, to ARC. And there they performed TTT on a fine-tuned Llama 3 8B model. And they performed kind of the natural sequence of steps that you would do if you wanted to perform test time training on few-shot learning tasks. So they generated several copies of the test task by leave one out mechanism and then added some additional data augmentations, rotation, etc. And then they use the next token prediction loss on all of the predicted outputs. And then in this way, for each of the test tasks, they trained a task-specific model. And then in this way, they were able to show really substantial gains. So here among, like, for example, on ARC, they saw significant gains, but also on Big Bench Hard, for example. And here is the gains shown over the base model and the fine-tuned model. In both cases, kind of base model is still shown the few-shot examples. So in that case, it's shown the few-shot examples in context. And the zero-shot baseline would correspond to the scenario where you prompt the model without any of the task demonstrations. Now, of course, the few-shot learning setting is a bit restrictive. So what do we do if there's no task-specific data given to us at test time? The natural questions are, can we select this task-specific data from our training data? Or can we even generate this task-specific data ourselves through interaction with an environment? So in these cases, what we want to do is we want to put the model itself in the decision-making loop. We want to allow the model itself to make decisions on what data to acquire and train on in the future. Now, why do we have to do this automatically? Well, I just want to kind of put test time training in a little bit of a broader perspective, which will illustrate why you kind of need the model to do this data selection and cannot have humans do this. So let's focus on language. So in language, you have all kind of the space of all possible token sequences. And what happens during pre-training is that there's some manifold that captures all of natural language. And pre-training learns this manifold. Now, next, we typically apply post-training. So we identify that there's some part of interesting language. And this interesting language is then learned during post-training, but it's typically still human curated. So you either have specific SFT data set, or you perform RL on a specifically curated set of examples. Now, test time training instead focuses on a particular interesting test task. But if you want to apply this at test time, you can't have kind of a human sitting somewhere and designing the data set. Instead, you would have to have the model selecting the data for you. So to understand different ways, we work quite a bit on this question of how can the model itself decide what data to use for test time training? And one first setting, which is quite interesting to understand, which we attacked first, was the question, can the model select data to imitate? So data from its training data set, pre-training data set, to imitate at test time. And one algorithm which we proposed there was SIFT. So SIFT selects the data that maximally reduces some notion of uncertainty. about how to solve the task. So intuitively, you can imagine some data manifold from which or within which your training data set lies. And then at test time, you get some prompt. And then SIFT would select the relevant but diverse set of examples which lie in your training data set. And this can be formalized in many different ways. One kind of nice probabilistic perspective to this is to formulate this as an objective which maximizes the information gain of from your next observation which comes from your training data about your prediction target, conditioned, of course, on your previous observations. And then we would perform the simple TT2 procedure, which just for everyone to remember, I'll quickly reiterate. So given a task, we find the local data, so the neighborhood, from a training data set. Then we fine-tune our pre-trained model on this local data to get a specialized model, fx. And then finally, we use the specialized model for the prediction. Now, to actually operationalize SIFT, we need two steps. First, we need to estimate this uncertainty, and we somehow need to make this tractable. So something which might seem natural to you now, given that we already started talking about the linear representation hypothesis, would be to approximate this model as some logit linear model in some known representation space. And in this case, we can actually bound the error of your model after you have trained it on n of your retrieved examples, error here in terms of TV distance, because we're predicting it kind of a distribution. We can bound this error by some scaling factor, which is independent on the test point and also independent on the data that we select. And it just depends on how close the pre-trained model is already kind of to the ground truth. And in quantity, which we call the uncertainty, which actually has a closed form, whose closed form depends on your pre-trained representations and also on the chosen data, which is here subsumed in the little n. Right? And the key insight here is that because sigma n is really the term that depends on the test point, but also on the data that you have selected, this term is the key term that measures how uncertain your model is about how to respond to X, or what is the correct label for X. And SIFT then performs kind of an iterative data collection. So we iteratively built this specialized data set by selecting the next data point, xn plus 1, such that the data set, including this next data point, xn plus 1, leads to the smallest predictive uncertainty. And then what's kind of nice is that in the simple setting with a linear function, the convergence of this uncertainty is guaranteed. And in particular, we characterize to what uncertainty you converge. And this uncertainty, we call it the irreducible uncertainty, depends on the available data. So of course, this uncertainty is larger if your training data set has kind of less of the data that you would need to make a good prediction. And it also depends on your pre-learned representations and how good they are in actually identifying the right data for you to train on. Now, in this project, we then applied this to language models, and then it was quite nice. We found a new kind of state of the art on the PILE benchmark. The PILE is a very diverse set of language tasks. And here on the plot, you see the next token prediction error, here measured in terms of bits per byte. And our method was able to outperform a much larger model, which was the previous state of the art. But going back, I want to go back to the takeaway that I mentioned earlier, and in particular, 2 points, which I think are critical in this takeaway. First, the question, are we limited to pre-learned representations? So in other words, I think this opens up the question, can we learn these representations over time? And then the second, I think, critical question is, can we obtain new data over time so that we're not restricted to the data which we already have? Now, on the first question, I just want to give a brief pointer. This is something that actually was one of the first kind of experiments that we conducted, which was quite eye-opening for me at the time. This is related to this question of, can we learn representations over time? And this is part of a NURB submission from last year. So let's suppose this is our representation space. The black dot is the point at which we're trying to predict. And the gray points are points which we should train on because they convey the right information But in representation space, they're quite scattered. So our representations don't really know yet that they are the right points to train on. So what we would actually want is we would like to push the representations such that these gray points are pushed more towards the black dot, right? And the question is, can we continue learning the right representations over time? And it was quite interesting for us to find that, yes, in some cases, this is possible. So what we did was we performed this sift on MNIST, but with a model from random initialization. So in this case, initially, the model's representations would be completely uninformative. You can imagine the sift objective will not be able to tell which points are good and which points are bad because we are computing this notion of information gain with respect to a model that was randomly initialized. But now we see here, and this is was the key insight, that the solid black line, which is if you select the data according to SIFT, significantly learns significantly faster than if you just perform IID data training. So IID data training meaning just randomly select data from your training data set. And this was surprising because this kind of means that over time, let's say after the first step, SIFT has retrieved uninformative examples, or at least not particularly informative examples for a downstream task. But now, still on this data, you perform some kind of learning. So you learn a little bit, your representations improve. Next time, SIFT will select more informative data. And again, your representations improve. And sort of this kind of bootstrapping seems to happen here. And we saw then similar results when we extended this to C4 later on. So now I want to for the end of this talk, I want to get back to the thing which I promised in the very beginning, which was to talk about challenging tasks. And I will not claim to talk about solving any possible challenging task, but I want to talk about a particular family of challenging tasks, which are sparse reward tasks. So these are tasks which require some chaining of very particular actions before you will observe any reward or any notion of success. So here are some examples. So point mazes, ant mazes, robotic arms. This is, of course, not an exhaustive list, and we'll talk about other settings as well. And the standard RL approach in these settings is to just repeatedly attempt the test task. So here you see in some kind of mazes on the right, see some visitation frequency plot or visitation plot of standard RL methods, starting from more on the left, more exploitative methods to more play and curiosity-driven methods, which explore a little bit more. But they are all each episode for them starts with having the goal of reaching the red cross, but you see none of them ever succeed. And they don't really seem to, even over millions, tens of millions of steps, don't really seem to get any close to, achieving the task. And this is really because, and this is very important, the agent never observes any signal before it solves the task. So the RL methods are stepping completely in the dark. And the only way they explore is either by adding some mostly by adding some random noise to the actions. That's not very informative. So clearly, to solve these previously unsolved tasks requires obtaining some new experience, new data, as I've mentioned before. So this requires some online interaction within your environment. And so what we asked in this project, this we will present at NeurIPS in this year, what we asked in this project is, what if the agent uses its current understanding of the task landscape to set itself informative tasks? So whereas standard RL, so here S0 would be a starting state and GH would be the achievable set of tasks. So where standard RL would just set the target task in every episode, and global exploration would set some diverse, uniformly directed frontier. What we propose and what we study is, can the model identify the right direction and then learn from tasks which are at the frontier of its current capability, but towards that direction? Now, the key question is, of course, how do you determine which tasks to attempt? And so what we do in this work is we learn a task condition value function, which measures the similarity of two tasks, G and G prime. And then we build kind of a task value, which is just an optimistic version of the value or the similarity of your starting state to your intermediate task. And so this is the task value. So this is how you want to select G. And in addition, the optimistic value or the optimistic similarity between your intermediate task and your target task G star. And these two terms are kind of traded off with this parameter alpha. So in some sense, the first term tells you to not take any tasks that are too hard, right? So that are similar enough to your starting state, but also diverse. This is kind of what the optimism brings to the picture here. And the second term kind of forces you to pick tasks which are in some sense similar, at least optimistically similar or related to your test task. And then, of course, we have this parameter alpha here. It would be nice to get rid of it. And the nice thing is you can auto-tune this parameter alpha to just have 50% task achievability. Because in RL, kind of you want to have 50% task achievability so that you can do the credit assignment efficiently. So you can kind of understand, well, what was good about the good attempts and what was bad about the bad attempts. And then what we see, and this is kind of what we see here, so the left three boxes are the exploration or visitation plots for other competing methods, which are all kind of undirected. And on the very right, you see discover, which much more efficiently kind of goes directly to the target. It's kind of in the beginning, the agent understands the structure of its environment, and then it just explores in the right direction. In the more complex maze, of course, it has to hedge its bets a bit more. And then once it understands, okay, I can go around the block, then it focuses on just going around the block. And this way, we see that the success rates are really dramatically better across both kind of simple and more harder high-dimensional robotics, navigation, and manipulation tasks in simulation. And so the red line is here discover, but kind of the baseline, and this is a little bit hilarious, but the baseline is standard RL plus curiosity, or the kind of standard based on what people normally do. And this stays flat at 0% success rate across all our tasks. Now, some few more observations from Discover. So one, it was kind of interesting to see, it seems that targeted exploration is really crucial in high-dimensional task spaces. So for example, we performed this experiment with point mazes. And here you see the number of steps in millions for reaching 10% success rate in point mazes of varying dimensions. And whereas like in two-dimensional mazes, undirected methods are still somehow competitive. But as soon as you go to multi-dimensional mazes, you need this targeted exploration. And in some sense, intuitively, at least in a cartoonish way, you can think about this discover exploration as kind of finding a one-dimensional tunnel around which you explore towards your target, right? That's at least the goal, right? You don't want to explore the entire volume of the search space. And then the second interesting observation was that Discover can leverage the prior knowledge about the task space. So one experiment that we conducted was we used the pre-trained value function from a point maze run, which was using the same layout as the ant maze. So we had trained the policy on the point maze with the same layout. And then we used this value to initialize the policy with the ant maze. Now, of course, the ant maze has a completely different actuators. The policy needs to be trained completely differently. But the value function already knew, okay, I can reach the goal by going to the top left. So this is the only thing I will explore. I don't explore the environment in any other way. Now, to wrap up, I want to talk quickly about extending this to language models and reasoning. So this is one of the last things we worked on, and it's still a preprint. So in this case, we basically tried to extend exactly this idea. So given a target task, we would try to build a curriculum of test tasks and then perform reinforcement learning on them to see if we can kind of hill climb and improve the model at test time. So what we do is at test time, we self-curate, or the LLM self-curates the test time curriculum of similar tasks for practicing. And this test time curriculum is selected with SIF to balance similarity to the test task and diversity. And then we train on this test time curriculum with GRPO. And the main results as follows. So you don't have to look into all of these in details, but we kind of covered a lot of benchmarks from math to code to general reasoning, and compared a model that was trained on the test time curriculum to a model that was trained generally with RL post training on the larger corpus, also to the base model, of course. And really across examples, we saw that test time curriculum led to significantly better performance. And in particular, if you look at the number of training samples that it takes to improve performance, the test time curriculum was much more sample efficient. So this is kind of our first big takeaway from this work, that the test time curriculum consistently achieves a higher pass at one than general purpose RL post training, and that it learns from significantly fewer attempts. Then we also wanted to look into how does test time curriculum RL compare or combine with other methods of test time scaling. So one very natural metric to measure the ceiling of a model is its pass at k performance. So this is the number, or this is kind of at a given k number of attempts, how is there any correct attempt or not in any of these k attempts, right? So at pass at one, this is of course the accuracy, but as you increase pass at k, it's just measuring, is there any correct attempt that you could extract downstream? And we see that with test time curriculum RL, this improves upon the base model, even for larger k. But kind of more striking was when we looked at the majority performance, so majority voting. And here you see, of course, in black, performing majority voting for a different case on top of the base model, and then in gray, performing majority voting on top of the post-trained model. And here we saw that even majority voting, like even the pass at one performance was better than the majority voted RL post-trained performance, but majority voting scaled quite well on top of the model trained with test time curriculum RL, meaning that it somehow, the curriculum taught the model some structure that it could exploit. And then finally, we compared two thinking models, where we saw that with curriculum RL, a model that was reasoning just over an 8K context window reached quite strong performance, and in many tasks very close to a model that was reasoning over a 30K context window. So in some sense, telling us that the model, through test time curriculum RL, learned how to be a better and more efficient reasoner within its limited context window. Right, so these were all kind of observations that told us that TTCs can possibly complement existing methods for test time scaling, such as majority voting and reasoning in context. Now, kind of the final thing which we wanted to ask here is, and this kind of goes back to what I started the talk with, do these TTCs actually specialize the models? And it was also interesting, it turns out in some sense they do. So what you see here is quite an interesting plot. So it's a kind of cross-evaluation plot. So the rows here correspond to models that were trained on a particular benchmark, or not on the benchmark, but the test time curriculum was constructed for that benchmark. So let's say the first row corresponds to the model that was trained for AIM24, and the column corresponds to the evaluation. And we see throughout that the model performs best, or the model for a given benchmark, the best performing model is the model that was trained for that benchmark with its test time curriculum. This was kind of the first interesting observation. So there seems to be some specialization happening here. And the other interesting observation is this block structure, right? You kind of see that models that are trained on math mutually generalize better to math. Models which are trained on code mutually generalize better to code. Interestingly, models that are trained on code kind of generalize better to math than vice versa. So you see that model that was trained on LCB has kind of better scores on math comparably than a model that was trained on AIM25 and is then evaluated on LCB. And then kind of one final ablation that we did, which this we did for AIM25, is we looked at different ways of performing test time curriculum RL. So one way is to just take the entire benchmark, say AIM25, that's 30 questions, and build one test time curriculum for these 30 questions and train on this. The other approach is to build a separate test time curriculum for each of the individual 30 AIM25 questions. And this is kind of the differentiation here between these two red bars. So the left red bar being the joint test time curriculum for all of AIM25, the right red bar being the test time curriculum for just the individual tasks of AIM25, and then the scores aggregated across the benchmark. And we see that there's even possibility for additional gains if you do the per task test time curriculum. And again, kind of showing here that both the benchmark level and the task level test time curricula are really outperforming the majority voting on top of the base model, even at very high K. So the takeaway of these is kind of that TTCs do, in some sense, specialize models to their target tasks. So to wrap up my talk, just a very brief conclusion. So TTT is a class of methods that specialize foundation models to individual tasks. And in this talk, I try to argue for the following two statements. So the first one being that TTT can enable models to outperform globally trained models, even if evaluated in distribution of the globally trained model. And the second one, that TTT does enable models to continue learning and improving at test time. Yeah, so I'm very excited to talk more and discuss more with all of you.